So, what we're going to do is recap chapter 8 and talk about what they did with single proportions, and then we're going to move into comparing two proportions. So, what we've got here is just kind of a introductory review problem. So, prior research suggests that 60% of young adults preferred Snapchat as their main source of social media, but some have suggested that this is declining. So maybe you're Snapchat and you care about the fact that people are moving to other social media platforms. Maybe you're a competitor of Snapchat and you're wanting to capitalize on them possibly losing interest in young users. Or maybe you're a parent who wants to keep up with what your children are using, so you're trying to figure out who's, using what social media platform the most. So what would your hypotheses be based on this wording? Well, the prior research shows that it's 60%, so our null hypothesis is that the proportion is 60%. And again, the wording of the problem indicates that we think it's moving or declining or becoming less than. So our alternative hypothesis would be that the proportion of young adults using Snapchat is becoming less than 0.6. So what you would then do, or what the wordings of problems we usually say, is that you took some sort of sample and you found some amount that prefer using Snapchat as their main social media platform. What we would then do is we would run that in this test statistic formula. We would calculate that z value. And what we need to focus on as we move into chapter 9 is that z value really uses the null data the majority of the time, or in other words, the null proportion the majority of the time. It says, okay, take what you found in your sample, the 280 over 500, compare that to the 60%, and make your standard deviation based on that null value. The 60%, its complement 40%, and then your sample size of 500. We're using the null value in the standard deviation because at the time, the null is what we would again maybe refer to as the assumed truth. So if it's what was true or what still may be true, then we should use that as our main source of standard deviation because, again, we're not sure if this is true or not true, but it's the best information we have. The sample is the new information, so we shouldn't be basing our standard deviation on the new information. So here's that all plugged in, and we get a z-value of negative 1.83, and we would then run to our z-table, find its associated p-value, and then make a conclusion from there. But let's look at the formulas for the test statistic of two proportions, because that's really all we need to focus on. The prompts, the wordings are really not going to change that much. It's going to move from, hey, young adults prefer Snapchat as their main social media platform and they suggest it's declining, to maybe something like compare the proportion of Snapchat users and Instagram users. We're just comparing two proportions at the same time, not one proportion to prior research. Two different samples comparing how similar or different they are. And so that's where we get this test statistic from. The test statistic actually, let me bring up these hypotheses. The test statistic relies on, again, the null hypothesis involving equality and the alternative hypothesis involving some sort of inequality, maybe greater than, maybe less than, maybe just not equal to. And that's not new information. But here's what the test statistic says. What used to be just a simple p hat is now the comparison or subtraction of your two proportions. So we're going to compare them, and notice what that comparison is then compared to afterwards. Hey, after you do your initial comparison of what you found in your samples, subtract that from or compare that to 0. Now this 0 is in place of the null proportion, or in other words, what the null hypothesis says. And why that 0 makes sense here is because we assumed, where the null says, that those two proportions should be equal. So when you subtract or compare two objects by subtraction, you would expect that subtraction would be 0 if they were the same. 5 minus 5 is 0. 20 minus 20 is 0. 80% minus 80% is 0. So if the null hypothesis says we need equality, then we're comparing the difference that we get from our samples to 0. And once again, the standard deviation on the bottom should rely somehow on the null hypothesis, The problem is these two proportions are equal, but our sample has some differences in it. What we end up doing is we form this new thing called p hat of c, or sometimes your calculator may just refer to this as p hat. But what this p hat's doing is it's adding all the successes from the first sample, all the successes from the second sample, and then dividing that by how many you sampled in total. And what that essentially does is this is in some ways the average of what we get from our two samples. Or in other words, what this does is it says, hey, anything you got, any difference you obtained in your first proportion and your second proportion shouldn't have happened because we thought these were equal. We didn't know what we were going to get before, so the best thing I can do to say what would these be if they're equal is essentially smash them together, so to speak. Let's just say, hey, all of this should have been the same, so whatever difference I get out of my individual samples is maybe just noise. This is what I should have gotten. Let's compare my two samples, their difference to what I should have gotten, this combined proportion. And that's why it has that C on the bottom. We kind of call it the combined proportion. All right, so let's put that in a word problem and see what that looks like, just with letters, and then we'll dive into your 9.1 homework. And of course, the p-value in concluding will be brought up as well. So maybe the word problem says prior research assumes that Westport and Vanguard students share the same proportion of upper level classes, but maybe we were interested to see if that's increased for Westport students. So before we thought Westport students and Vanguard students had the same proportion of advanced students, but maybe now we start to think that Westport students have become more advanced, because of course we have. So this is what the test statistic would look like. It's a z-value, and we would then, again, take a sample of, 20 or 50 Westport students, maybe 100 Westport students, and find out how many of them participate in these upper level classes. Do the same for Vanguard, and of course, again, compare that to 0, because we thought that they were going to be equal. We thought that we would see no difference in them. Then, again, what we would do is we would take all the successes from Westport, all the successes from Vanguard, or in other words, how many are in upper level classes in our samples from Westport and Vanguard, and divide that by how many we sampled in total from Westport and Vanguard, because this is what we're going to assume the equality is between the two. This is our combined C. This is what we would expect to get if they're the same. Any difference we find is just noise. And this looks a little bit interesting, the way it's 1 divided by n of Westport, 1 divided by n of Vanguard. But really, this is just mathematicians being lazy, because if I cut this around and move it a little bit, this is really what that formula looks like. It really, in actuality, has both fractions they're multiplying. So when I read it like this, it definitely looks a little bit more familiar to this standard deviation. There's a p hat, a 1 minus p hat over n. It's just that when we have two of them, you end up with p of c, 1 minus p over c over both fractions, and mathematicians are lazy, so why write p hat of c, 1 minus p hat of c twice? If it's the same thing in both fractions, why not just distribute it and put it out front, but it's still in the square root? So with that being said, this is the new formula we're going to be dealing with, but how we word hypotheses, how we find p-values, and how we ultimately conclude isn't necessarily going to change compared to what we saw in Chapter 8. Except for one additional thing, and that's that we can also draw our conclusions from confidence intervals. And I think we'll just save that for when we see it in the homework, and then we'll proceed from there.